Okay, let's give me a minute.
Yeah. Okay.
Yes.
Perfect. Okay. So welcome everybody. It's a great pleasure to have today Tuan Tran, who will talk about intersection of hypergraphs. Please, Tuan.
Thank you, Benny, for the invitation. And today I will talk about these intersections of hypergraph. And this is I work with Diệp Lương and Di Long. So Di Long is my PhD student in China, and Diệp Lương with next semester she will be a PhD student in Columbia University. So let me start with some very briefly about the history of the problem, and then I will state our contribution, our main result, and then maybe I will give you a sketch of the proof, and at the end I will mention some open problems. So the concept of hypergraph discrepancies was introduced in the 70s by Erdős and Spencer, and they ask us these very natural questions. So we have a graph G, and we want to know how much the induced subgraph of G deviates from the expected size. And we can quantify this more formally. We can make this diagrams as follow. So now we have a K-uniform hypergraph G with n vertices, and the S density of G is P. So P is the number of edges of G divided by n choose K. The discrepancy of G is defined as this maximum. And so let me explain. So this is the number of edges. So wait a minute. So this is the number of edges induced by U, and this is the expected size, the average.
One, we didn't hear you. One. How do you hear us? Something probably happened with the internet. So let's see. Maybe Tuan comes back. Let's wait. Kwan. Yeah, sorry everybody, it seems that Kwan has some computer related problem. Hopefully. I had to send him an email. Let's see. Kwan? Yeah. Maybe let's wait a couple of minutes here. Quite understand what.
So I got a message that my iPad was not connected to Zoom.
Yeah, but what this means your iPad not connected to Zoom, but maybe, you can connect it to Zoom, or maybe you can move Tuan, maybe you can move your talk to the computer.
Yes. So let me use my computer.
Yeah, I mean, I don't know your iPad, but it's.
So when does it stop?
Yeah, so I did that multiple participants can share simultaneously, so you should be able to share your screen. Can you share your screen?
Yes, I can.
Yes, so we see your screen. So since you have slides, it's not such a problem. Then maybe you will just don't use this right thing. Yeah, we see it. So then now move just my video to the side, okay? Let's go back. Okay, very good. So can we continue?
Yes. So where did it stop?
You want the first slide, please.
First slide. Good.
Yes, here. No, here. Right. So you were explaining us that the discrepancy is difference between what you expect in random graph, hypergraph of the density and the number of edges. Okay.
Okay. So maybe from time to time you can ask some question to make sure that you can still hear me.
I will ask questions the minute we will don't hear you, but maybe let's continue.
Okay. So so for example, when G is empty, then this discrepancy is zero because the density of the empty graph is zero, and any vertex induce zero h. So the discrepancy is zero. And similarly, for complete graph, the discrepancy is also zero. And another maybe less boring case is when the graph is random. So we consider Z to be the endogenous random graph, for example, where each pair of vertices is selected as an edge with probability P. Then by concentration inequality, we can show that the discrepancy of this random graph is about n to the 3/2 in the graph K, and in the hypergraph K, it should be n to the K plus 1 over 2.
Mm-hmm.
And now, and in 1971, Erdős and Spencer proved that any n vertex graph G with the density exactly half, must have discrepancy at least n to the 3/2 in the graph K, and in the K uniform hypergraph K, it should be at least n to the K plus 1 over 2. And as I have mentioned it before, this bound is best possible by considering the random graph. In the graph K, that is when K equals 2, this result of Erdős and Spencer were extended to all densities by Erdős, Pike, and Spencer. So they proved that if G is a graph with density P, then the discrepancy of G is bounded from below by roughly n to the 3/2. And here, the S density P is a constant. So this works even for smaller P, but for this talk, I will only focus on hypergraph or graph of constant density. And later, Bollobás and Scott extended this result to all uniformity. So they proved that for any uniformity K greater or equal to, and any S density P, the discrepancy of a graph hypergraph G of a K uniform hypergraph G with S density P must be at least n to the K plus 1 over 2. So for dense hypergraphs, we now understand the discrepancy pretty well. And motivated by all this work, Bollobás and Scott introduced the concept of discrepancy for pairs of hypergraphs. So you can still hear me?
Yeah, we hear you, don't worry.
Oh, okay. So now we are given two K-uniform hypergraph G and S with the same number of vertices N, and the corresponding densities are P and Q. The discrepancy of this pair is defined to be this quantity. So let me guide you through these definitions. So here we have the maximum is taken over on G prime, which is isomorphic to G, and G prime have same vertices as S, and we look at the difference between the number of edges in the intersection of G prime and S, and the expected intersection size. And by taking S from a specific family, we can get many interesting graph parameters of G. For example, if let's consider the graph K, and we take S to be the complete bipartite graph K and half, then the discrepancy of the pair G and this complete bipartite graph is the so-called bipartite discrepancy of G. This was introduced by Erdős et al.
So, it's symmetric, right, the relationship. I can fix G and then take a best, because it's just permuting the
Yes, this is symmetric.
Okay.
So this I just want to bring them to have the same vertex set, and then I permute the vertices of one of them. So this definition is symmetric. And if I let Sm to be the graph obtained from by adding this n minus m isolated vertices to a click on m vertices, then the discrepancy of this pair G and Sm is. So now if we look at let's going back to the definitions. We should take this maximum over on isomorphic copy Z prime of G and look at the intersection of G G prime with Sm. So we only need to care about the locations of the vertices of this Km. And so this will become the number of edges induced in G induced by the vertices of Km. And the second term, PQ times n choose 2 become P times the psi of U choose 2. Because here Q times n choose 2 in the graph K is the number of edges of H, and if this K is the number of edges of Sm, which is M choose 2 or U choose 2. So in this special K, the discrepancy between G and Sm is simply this quantity. And by taking the maximum over on M, we will recover the discrepancy of G. And you can also see from this argument that any lower bound on the discrepancy of the pair G and Sm will give us a lower bound on the discrepancy of G. think that's one of the motivation for studying the discrepancy of a pairs of hypergraph or of graph. And the Bollobás and Scott proved that if G and S are graphs with moderate density, so the density of G and S are bounded away from 0 and 1, then the discrepancy of the pair is bounded from below by n to the 3/2. And here the hidden constant here depend on the densities of G and S. This from the previous argument, from this argument, we see that the new result implies that the discrepancy of any graph of moderate density must be bounded below from n to the 3/2. So the Bollobás and Scott result implies the earlier result by Erdős in the graph case. And they conjecture that this result should extend to hypergraph. And more precisely, they believe that if G and S are two k-uniform hypergraph of a moderate density, then the discrepancy of the pair is bounded from below by n to the k plus 1 over 2. This conjecture, if true, would imply on the previous result for the discrepancy of hypergraph. But unfortunately, they found a counterexample for the 3 uniform case. And we managed to extend their construction to the counterexample to all uniformities, at least 3. So somehow the 3 uniform case behave very differently from the graph case. Since the example, the counterexample is quite simple, let me briefly tell you the constructions and explain how to extend it to all uniformity. So a Steiner triple system of order n is just a 3 uniform graph on n vertices, where each pair of vertices is contained in exactly one edge. And their construction is just like this. We take Z to be an edge-disjoint union of linearly many Steiner triple system of order n. It is well known that we can pack linearly many Steiner triple system into the same vertex set of order n. And they take H to be the complete bipartite 3 uniform hypergraph. So this have, so the vertex set of S have 2 parts. One has size m and the other has size n minus m. And on the edges must intercept both parts. And let us see that the discrepancy of the pair G and S is 0. So this would give a counterexample to their own conjecture. So now we consider any 3 graph G part. Yes.
Can I ask you, so this H is, you have 2 parts and you take all the edges which have vertices on both sides, right?
Yes, in both sides. So it have 2 in one side, 1 in the other.
And what is exactly the number you're comparing to? Like,
so m is linear on n. M is, let's say, n over 10. So it's,
like, is there an obvious formula from just the density of G and the density of H to get what is the expected dependence,
yes,
discrepancy in their conjecture?
Yes, we don't even have to compute the.
Okay. Just curious, what is the formula? I know it's, yeah. Thank you.
Yeah, so it is dense. So because each kind triple system have about n square as is. So Z will have about n cube as is. So Z is dense. And S is also dense. If M is linear on N, then the number of edges of S is also cubic in N. So both Z and S has the moderate densities. And to see that the discrepancy is zero, we don't even have to compute the density. Of course, for the conjecture, we need to check that the density is bounded away from 0 and 1. And from the definition, we only need to consider a 3-graph G prime, which is isomorphic to G, right? And which have the same vertex set as S. And we look at the intersection of G prime and S. And you see that's, so M choose 2 is a number pair of vertices in the first part. And because this is this joint union of Cn Steiner triple system, right? Each pair of vertices from the first part is contained in exactly Cn triple in G or G prime. And similarly, each pair of, yes.
But didn't you need the Cn vertices to be completely inside this n minus m vertices?
Good question. Okay, actually, yes, so the calculation is, this formula is on. So we take because the intersection on the axis of S line must intersect with both parts. So we consider pair, one from the first part and the other from the second part.
Yes, and then it doesn't matter where the third vertex is.
Then it doesn't matter. Because each pair is contained in Cn. So the formula should be n times n minus m times Cn. Yes, so at least someone follow the understand this construction. Okay, so because this because this the intersection size is a constant, right? So the discrepancy is 0.
That is it clear for everybody, right? So you just take if one vertex from one part, one vertex from another part, it's m times n minus m, and every such pair is extendable to triple, and this triple will go across, just to make sure, right? If that question, please ask, it's indeed mistake.
Yes. So the formula is wrong, but the examples still stand. Explained by Benny. Okay, so this can be easily generalized to all uniformity. So we construct a counterexample for all uniformity because we simply because there is a natural generalization of Steiner triple system. So we have this Steiner triple system. So for any t, k, and n, a Steiner triple system S, t, k, n is that a k-graph, k-uniform hypergraph on n vertices, in which each t subset of vertices is contained in exactly one edge. And Kwan and Mycroft prove that we can have linearly many edge disjoint union of Steiner system. So actually here we should take t to be k minus 1. And we denote the resulting k uniform hypergraph by G. So G is a F disjoint union of linearly many Steiner system as k minus 1 k in n. And let's S to be this hypergraph. It has the k minus 1 path, and on the edges must intersect on the path. Then by the very same argument, we can show that the discrepancy of G and S is 0. Moreover, the density of Z2 hypergraph are bounded away from 0 and 1. So we have seen that by the Bollobás and Scott construction in the 3 uniform K, and by our construction in on uniformity, we see that 2 hypergraphs are not enough to guarantee a large discrepancy. So the questions which were actually asked by Bollobás and Scott is that how many K uniform graphs are enough to guarantee that some pair has large discrepancy. And for this, we denote this quantity by fk. For any k, at least 2, we let fk be the least integer m, at least 2, such that any set of m k uniform hypergraph on n vertices with the density bounded away from 0 and 1 must contain a pair with discrepancy greater than n to the k plus 1 over 2. And we have seen that F2 is 2. So 2 graph is enough. But we also have seen by our construction that 3 hypergraph is not enough. So fk is at least 3 for every k, at least 3. So this is a low bound. From the upper bound, Bollobás and Scott prove that fk is bounded from above by k plus 1 for all k at least 2. And in some sense, this upper bound is best possible. So and it is best possible for weighted k graph. I just briefly mentioned this. I will not explain what is the discrepancy of a weighted k hypergraph.
So just if you have 3 uniform hypergraphs, then whenever you have 3 of them, you already have a discrepancy as conjectured, right?
Yes, that's what we prove.
4, right?
4. But we prove that actually 3 is enough.
I see. Okay, so that's the next theorem.
Yes, so this is say that 4 is enough, but actually 3 is best possible. And so here so as I said, this is in a sense best possible for weighted k hypergraph, because they also prove the very similar the same upper bound for weighted k graph, whatever that means, and they also prove that there exists k uniform weighted hypergraph such that the discrepancy between any pairs is 0. And so recently we managed to prove that fk is equal to 3 for every uniformity k between 3 and 14. So 3 k uniform hypergraph is enough to guarantee a pair with large discrepancy when k is between 3 and 14. And for Zener k, we have this upper bound, which is much smaller than this linear upper bound. So this is optimal for weighted hypergraph, and for unweighted, so we have this separation. Our bound is separated from this bound. And actually, assuming some very difficult number theoretic conjecture, our proof give an upper bound of polylog on K.
So you say it again, only log?
So assuming some number theoretic conjecture, our proof give an upper bound of polylog.
Polylog.
And actually
And
numeric experience, so there's just our proof give a constant upper bound. But we don't know how to prove it rigorously. So it could be well be the case as Fk is 3 for every k, or at least Fk is bounded by a constant for every case. And to illustrate the proof, I will consider a weaker versions. So we consider this F star of k, where instead of guarantee requires a pair with large discrepancy, I only require that the pair have positive non-zero discrepancy. So in the definition of Fk, we require this, the pair have a density, has large discrepancy. Right? So clearly from the definition, F star of K is upper bounded by Fk. So any upper bound on Fk would be an upper bound on F star K. But not vice versa. So I will give an overview of the proof, how we can prove an upper bound on F star K, and later if I have time, I will explain how to modify it to get an upper bound on F of K. So let me give the overview. So we have a K uniform hypergraph G with vertex set V and S set E. And V has n vertices. And I will denote by 1E to be the indicator of the F set of G. So it is a function from V choose K to 0 or 1. It records whether a K set of vertices belong to G or not. And the key concept for us is the so-called the W vector of this hypergraph G. So it has K coordinates W1 to WK. And the D coordinate of this W vector is defined as by this cumbersome formula. So let me guide you through these definitions, and let's focus on the graph K first. So now, here so first consider when in the graph K, so we have only two coordinates, right? W1 and W2. And let's first, so here K is 2, and let's consider the K when D is 1. So the first term will be, this term will be 1 over n cubed. And we should consider the sum over on sequence of 2D distinct vertices. So when D is 1, then we need to consider two on possible two distinct vertices, H1 and Y1. And for any other vertex in the graph, this pair we have sign plus, and this pair we have sign minus. And so here the sum is run over on set A, which so run over on two set, right? So it run over on pair of vertices, and I intercept with H1 and Y1 in exactly one element. So it must on the pair have this form. So this will be so this pair intersects with I1 y1 at 0 point, so it have plus sign, and this intersect in this have contain y1, right? So this have minus sign. So if this is an S, then it will contribute plus 1 to this sum, and if it's a non-S, then it contributes 0. And if this is an S, then it will contribute minus 1 to this sum, and it will contribute 0 if it is a non-S. So W1 of G will be this sum, the sum over on pair X1, Y1 of the degree of X1 minus the degree of Y1. And the second coordinate W2 of G. So for the second coordinate, we need to consider on sequence of 4 distinct vertices H1, Y1, H2, Y2. And this sum will become this 1 over n to the 4 of this sum over all possible H1, H2, Y1, I2, and this, and then we have this alternating sums. Because here, if we look at for example, look at the pair Y1, Y2. So because the set I must intercept I at exactly 1 point, right? So I must be one of these 4 pairs. And for the pair I1, I2, because I intercept I1, I2 as 2 elements, this intersection is 2, so the sign is plus 1. And similarly, we get on the other term. So we have 4 terms in total. And okay, so this, okay, let me make another remark. This is just a normalized factor to make sure that WD is bounded from above by a constant. So we should think of WD to be just as a number between 0 and 1.
Sorry, Kwan, just to understand. So here
Yes.
in the for W2, you want to say the number of common neighbors of Y1 and Y2, or because this 1E like just measures if there is an edge between Y1 and Y2?
Yeah, like instead of 1 to E, you just mean like kind of the codegree, right?
Yes, exactly codegree. Yes, this is codegree.
Okay, thank you.
Yes, but because in the graph case, and there is just 1 if Y1, Y2 is an S, 0 if it's not an S. But in general, this will be the codegree. Yes, thank you. This. And our proof relies on this inequality by Bollobás and Scott about the discrepancy of the pair in terms of the W vectors.
And it's just so the proof comes from the placing one graph randomly on top of the other.
The proof of this inequality.
Yes.
Yes, but it's quite, yes, the proof is because we also need to analyze the effect of switching to vertices.
Mm-hmm. I see.
So it is fairly complicated, I think. But of course, they estimate it by estimate some expectations. But analyzing that expectation is quite difficult. And so, okay, so so from this key inequality, we see that if the maximum, if for every k-graph of moderate density, we have this this property, the maximum, the top k minus r plus 1 coordinate of W has a non-zero element. Then we can upper bound f star of k by k minus r plus 2 by pigeonhole principle. Because here we have from r to k, we have k minus r plus 1 coordinates. So if we have k minus r plus 2 hypergraph, then we can find a D. So that's the corresponding WD of the two hypergraphs are positive, are both positive. And so by this inequality, if WD of G and WD of S are both positive, right, then the discrepancy is positive. So to prove any upper bound of this form, k minus r plus 2, where r is some function of k that we want to have, then it's enough to prove this for every k uniform hypergraph of moderate density. So one of the top k minus one of the first or one of the last k minus 1 plus 1 coordinate of the W vector must be positive. That's enough to guarantee this inequality. So putting it differently, to prove this upper bound, we need to rule out the possibility that all of these coordinates are zero. If we can rule out this, then it means that the maximum, then one of them are positive for any k uniform hypergraph of moderate density. So this is kind of just forward from the Bollobás and Scott inequality. And we make these crucial observations. Actually, we can characterize. We have an algebraic criteria for this this condition. If all of these coordinates are zero, then we can find functions on r minus 1 tuple, so that for all a, 1EA can be written as the sum of SS, where S run over all subset of psi r minus 1 of A. And you can check this for the graph K. For example, the graph K, we have this. Yes, so we have H1, Y1, H2, Y2. And here, if we have f of y1 plus y2, then we minus f of h1 plus fy2 minus f of y1 plus f of h2, and we plus f of h1 plus f of h2. Then this becomes 0. And we prove that this is the only possibility. So this is the higher inclusion matrix. So it is some linear algebra. And more importantly, these conditions, this is a local property. So it's only it's a local property. And in particular, if G satisfies these conditions, then the same holds for all induced subgraph of G. simply because this is a local conditions. And it allows, because this is a local property, it allows us to take a local approach. So actually, it's Conlon, Faust, and Benny proves that every K-graph of moderate density must contain an unavoidable pattern. So which means that G must contain some unavoidable pattern, and because this local property, that unavoidable pattern also satisfies this property. And this is a precise definition of unavoidable patterns. So K is a uniformity, and L is a number of paths, and F is the size of each path. So a KLS pattern is just a K uniform graph. F satisfies these three conditions. F is neither empty nor complete, because we want F to witness the fact that our graph, our hypergraph G has a moderate density, right? So we don't want F to be either empty or complete. And moreover, the vertex set of F can be partitioned into L paths, V1 to VL, each of size S. And moreover, this the indicator evaluate at any K element set A depends only in the intersection type. Depend only on the intersection side of the intersection of A with V1 and so on, and the side of the intersection of A with VL. And Conlon and Faust and Sudakov prove that so for every K and S greater than 2, there exists and not enough such that every K graph of moderate density with at least n naught vertices must contain a KS pattern. So a pattern, a K uniform pattern with K path. So in summary, if we can prove that the maximum is strictly greater than 0 for all unavoidable pattern F, then this automatically translates to an upper bound on F star. And we actually we can prove this, and our general strategy is to use induction on the pair KL. So we not only prove this for KS pattern, but we need to prove this for KLS pattern. And we need to induction on the number path L. L is between 2 and K. And it turned out that the by K, the bipartite K is a hard disk K. And the bound comes from this bipartite K. So let me very quickly kind of explain what is the method here for the base K. So we consider a bipartite pattern. So the number path is 2, and this pattern is, we have a K uniform pattern. And for every alpha between 0 and K, I denote by X alpha to be a binary bit. We record where the K set with alpha element in the first part and K minus alpha elements in the second part of F is an edge of the pattern F or not. And this because by the definition of pattern, this does not depend on the choice of A at all. And from the algebraic conditions, so remember that okay, let me return to this slide. We have this algebraic condition, right? And from these conditions, we can find the linear relation between this binary bit. And so it turns out that one can show that the binary bit X alpha satisfies this system of equations. And we can prove that using some elementary number theory. We can prove that if alpha is at mod k to the minus k to the 0.525, then this system of equation only have trivial solutions. So on the i's are the same. But what does this mean? If all of them are zero, then f is empty, and if all of the xi are one, then f is complete, which is not possible, right? Because we require f to be non-empty and non-complete. So where does this number come from? So why we need R to be this? Because we use we know that between k and this number there is a prime number. And let's say if m, so m is between R and k, and let's say m is a prime, or m is p minus 1, where p is a prime, then by Lucas' theorem, we know that p minus 1 to alpha is congruent to minus 1 to the okay, sorry, this is minus 1 to the alpha. Then this will be congruent to minus 1 to the alpha modulo p, if m is p minus 1, where p is a prime. So this will become 1, and we will have the sum of p numbers, p0 or 1 number, which is congruent to 0 modulo p. So all of them must be 0 or 1. So that's how we have this bar.
Tuan, can I ask you?
Yes.
So this is the proof, but if I want, so what you believe about this equation, right? So under which condition it has only trivial solutions?
So actually, if we assume the Kramer conjecture about the gap between consecutive primes, then this will translate to if the conjecture is true, and if the gap between two consecutive primes is about log square, then we could get an upper bound of log square.
Yeah, no, I understand that, but maybe there is some way to kind of address it. Not.
Yeah, so we run some calculation in computer, and it seems that for k up to the hundreds, we always get an upper bound of 4.
Mm-hmm.
So the lower bound is 3, and probably the upper bound we can get, or probably the upper bound should be 4 from our method.
Mm-hmm. I see.
But our method, but to prove that f, okay, to prove that f of k is 3 for every k, then we need a new idea, because I think our bound can only give an upper bound. Our proof only give an upper bound of 4. Because simply because in okay, I can tell you, because when k is 15, then this k is 15, and r is k minus 1. So if we want to get an upper bound of 3 from our method, we want r to be k minus 1. but when k is 15, then this system of equation indeed has non-trivial solution.
No, that I understand, but I'm just saying, look, if you want to prove this big O1 bound, let's say, just for the even simpler problem, for this F star, this is just equivalent. So you take the system, you show that
Yes.
this system has only trivial solution.
Yes.
Right, for R, I don't know, K minus 100, and then,
yes.
Let's see, okay.
And actually, to actually get an upper bound on the original function f of k, we need a robust version of all of our arguments. So, for example, I can make a very quick comment. So this k inequality is good because in the worst case, d is k, then this term is if d is k, then this is n to the k plus 1 over 2. So this is good. But we need a robust version of this. Like instead of bigger than 0, we need it to be bounded away from 0. So in order to do that, we need a robust version of this. So say if all of the WR to WKs are close to 0, right? We must prove that we can find a function f such that the indicator is approximately the right-hand side. And we managed to prove it using Fourier analysis. And for using Fourier analysis, this definition of double vector is not suitable. We need to use its L2 version. And another part that we need to have a robust version is this unavoidable structure. And because here we only need to get some stability version, right? So in the unavoidable pattern result, we must allow some small fraction of edges to be kind of uncolored and still be able to find this unavoidable pattern. And it can be done. So we use some of the ideas from our paper, from the paper with Matthew. Okay, so the conjecture is it seems plausible that the f of k is always bounded from above by an absolute constant. But can we prove that actually it is 3, fk equal 3, let's say for infinitely many k? Because certainly our method does not give this result. Okay, so thank you, everyone.
Thank you very much, Tuan. So I guess people already asked questions, but are there more questions? Okay. So I guess we asked most of the questions already, Tuan. So thank you for interesting talk and actually very puzzling result in the sense that the system looks very surprisingly simple that it's hard to show that it has only trivial solution. But of course for the equations that of this high involving these binomials, it can be. So it's actually some good thoughts for people who came to your talk. So thank you very much again. We can stop the recording.